Hi all. So today we will talk about exercise 3.62, radius of curvature. And we have this concept about radius of curvature. What is it? Let's go on to Wikipedia. Well, according to Wikipedia, the radius of curvature, r, is the reciprocal of the curvature. And what is that exactly? Well, basically it means that if we have a curve of some sort, and then let's say call this point P, and we draw a circle that best approximates this curve at point P. And the radius of that circle is called the radius of curvature. And the question is basically asking us to find the radius of curvature. So let's try to do that. Part A asks for the radius of curvature at the top. Well, at the top, let's say it's here. I already drew a circle, and then we have this radius r. What do we know about the projectile at this point? So let's first write out the formulas for velocity and acceleration. So velocity is v naught cosine theta, comma, v naught sine theta minus gt. And then a is basically 0, negative g, since there's no horizontal acceleration in projectile motion. There's only the acceleration downwards due to gravity. And then at the top, we also know that Vy at the top is 0. So this makes the question a lot easier. So it is V naught cosine. So at the top, V is V naught cosine theta, comma 0. And then acceleration is just 0, comma negative g. So how is this going to help us? Well, let's see. We drew a circle here that best approximates the curve. Although the path of this projectile is a parabola, not a circle, if we zoom really into this diagram, then the circle basically completely matches this segment of the curve, the circle that we created. Then can't we say that the behavior at this point, at least locally, it is a circular motion? I'm not saying that the entire motion across the whole path is circular. Only at the specific point on the parabola, it is behaving like as if it's in circular motion. So then the acceleration must satisfy the magnitude of the acceleration, which is positive g, because it's the magnitude. It needs to be equal to v squared over r. And we know v squared from here, that's v0 cosine theta. So v naught squared cosine theta squared over r. That's the radius of curvature we're trying to find. So, and then we just isolate r. We get r equals to v naught squared cosine squared theta over g. And so that is our answer to part A. Now let's look at part B. It is asking us for the radius of curvature at the beginning of the path. So let's use the same logic as before. We view it as, so like the circle here, we view it sort of like going in a circular motion locally, just at that point. We can see it as going in circular motion. So then what do we need? We have the formula a equals to v squared over r. We just need to get a at the beginning and v. So we knew that v is v naught cosine theta, comma v naught sine theta minus gt. And then acceleration is the same thing, it's 0, comma negative g. And because it is at the beginning, we can say that t is very small. And so this gt term, we can just ignore it. So then v just becomes, so at the beginning, we can say that v is just v naught cosine theta, comma v naught sine theta. And then acceleration is still the same thing. And we also need to be careful of one more thing, because we're at the beginning here, not the top anymore. So this is theta, let's say this is the beginning. And then we draw a circle that best fits the curve. Note that gravity is pointing downwards this time. So we cannot do it like before, where we just did g equals to v naught squared cosine squared theta r over r. So we need to get the radial component of gravity. So let's say if this is the center, we need to get this component of gravity. So how can we do that? Well, let's look at this triangle. You have gravity, and then let's say the center of the circle is here. The radial component points towards the center of the circle. And then there's also the tangential component. We know that this is a right angle because, well, the radial direction and the tangential component is always perpendicular. And we need another angle theta, or some sort of known angle. How can we do that? Well, because this is a circle here, right? And we have a tangent. We can say the tangent, we know that the tangent and the radius of the circle at that point is always perpendicular. So how is that going to help us? Well, let's see. We have the circle here. And then we know that this is perpendicular. And then you have this is also perpendicular. And we know this is theta. Well then, if we look at this triangle, we know this is a right triangle. And then so then this angle will be 90 minus theta. And so this angle here would just be theta, because their sum is 90. They need to be 90. So then now we know this angle here is theta. So then the radial component of G, or of A at that point, is, using trig, we get G cosine theta. It should be negative G cosine theta. And then we know that A needs to be equal to V squared over R. And remember, it's the magnitude here we need to use. So it's going to be positive G cosine theta. And what's V squared? So we know V is this. What's the magnitude of V at the beginning? At the beginning, the magnitude of V at beginning is square root of V0 cosine theta squared plus V0 sine theta squared. And then, because we're using V squared here, it becomes G cosine theta needs to be equal to V0 squared cosine squared theta plus V0 squared sine squared theta over R. And now we have, so this just becomes V0 squared sine squared theta plus cosine squared theta over R equals to G cosine theta. And so we know this by the identity, this is 1. So then we just have V0 squared over R equals to G cosine theta. In fact, we didn't really even need to write this, because, well, we just know at the beginning, when t, the time is very small, V is just basically the magnitude of V is just V naught, right? Because it's at the beginning and V naught is the initial velocity. And so we have V naught. So V squared becomes just V naught squared over R equals to G cosine theta. So what is R here? Well, R just becomes V naught squared over G cosine theta. And that is our answer to part B. For part C, the question is asking us for at what angle should the projectile be fired so that the radius of curvature at the top equals half the maximum height as shown in figure 3.35. So let's try to first derive the formula for the maximum height. So imagine a projectile fired with V naught and then you have theta. So we know that at the top the y component of the velocity is 0. So what is Vy? Well, Vy is just V naught sine theta minus gt. It needs to be 0 because at the top there's no y component. The y component is 0. So V0 sine theta equals to gt. T is just V0 sine theta over g. And then we know that the height formula is just y naught. The changing height is y naught plus V0 sine theta t minus half gt squared. And let's call like the ground level to be just y equals to 0. So y naught is just 0. So it becomes V0 sine theta t minus half gt squared. And so we know t, we just plug in this formula to here. We get V0 squared sine squared theta over g minus half times g times t squared, which is g squared over V0 squared sine squared theta. And this cancels, and we have basically from here we have half V0 squared sine squared theta over g. And so that is the maximum height. So let's call it capital H. That's the maximum height. So y max. And what can we do with it? Well, we knew at the top from part A, the radius of curvature is V0 squared cosine squared theta over g equals to radius of curvature. So then we just have to plug in the half the maximum height into R, and then we will try to find theta. So we got this one here. So what is half the maximum height? It's just a quarter times V0 squared sine squared theta over g. That's half the maximum height. And that thing, that's just basically the R. So R equals to a quarter V naught squared sine squared theta over g. It equals to, so part A we have V0 squared cosine squared theta over g. So V0 squared cosine squared theta over g. So now we try to solve for theta. How can we do that? Let's see. Let's remember that tangent theta is just sine theta over cosine theta. So we have sine squared theta. Let's move cosine squared theta to the left side. So we have sine squared theta over cosine squared theta times a quarter V naught squared over g equals to V naught squared over g. And then we just move this whole thing to the right. We have tangent squared theta equals to 4 times 1. So just tangent squared theta equals to 4. Using our calculator to find what theta is, we get theta is approximately 63.4 degrees. And that is our answer to part C. Thank you for watching.